Okay, first thing I notice about this, to me, these look like guitar strings. I don't really know what's going on up here, but my just first instinct is like guitar strings. Don't know if I spelled guitar right. Deal with it. All right, guitar strings. Guitar, question mark? I know guitar would have 6 strings. This only has 4, but still. Okay, so I've got an oscillator, and this has a figure above shows a string with one end attached to an oscillator. Okay, so that means that this is definitely fixed. Sorry, I'm writing with a mouse. And the other end is attached to a block, but that block's hanging. Hang on. The string passes over a massless pulley. Okay, that means the string and mass are probably free to move, which turns with negligible friction. My first instinct says free to move, so that this might be open. But if that is a particularly heavy block, if this big M right here is really big, that could pull that string totally tight to where it might be fixed. Open, question mark, fixed. That's important because if it is fixed, just put F, F. Remember the first harmonic. I'm going to draw this like a tube because it's easier. It's like a closed tube. That means your first harmonic will be very different than if it's the oddball fixed open. I don't know yet. See, because these two sides would be closed. If this were a tube, this would be like fixed open, and that's the oddball, meaning you can only have odd harmonics. So like fixed, you have node, and then your antinodes in the middle. So that is lambda over 2. You get half a wavelength in one tube. Whereas if you have the other one, remember you have node, antinode down here because it's got to be open where it's open. And so you're counting by quarters and you have odd only, no even harmonics. Okay, but anyway, let's see what they say. 4 such strings, A, B, C, and D, are set up side by side as shown in the diagram below, the one that looks like a guitar. Each oscillator is adjusted to vibrate the string at its fundamental frequency. Okay, so each string I'm noticing has a fundamental frequency. And remember, fundamental frequency just means first harmonic. That's the frequency that causes the first harmonic. I'm just going to abbreviate first harmonic. So they're all different. And these letters make me think even more about like a stringed instrument. They have, thickness of string. That's always different if you've ever seen a stringed instrument up close. Thickness of string. Lots of question marks here. Okay, let's see. The distance between each oscillator and the pulley is L. So see, this is kind of like the center. This goes down to the center of the pulley on all of these, and this goes to the center of the pulley on this. Those are the same length. So, and the mass of each block, so big M is the mass of the block. That's important. Okay, is the same. However, the fundamental frequency of each different, so that's a lot to think about. Okay, the equation for the velocity v of the wave on the string is velocity equals the square root of force of tension over mass over length. Okay, they'll tell us what all this means, where Ft is the tension, force of tension, good, of the string, and M over L is the mass per unit of length. Okay, so that's like if you just like slice something up, how much each little slice would be, how much mass that would be. The linear mass density. For a string, okay, each little slice of string would probably look the same. So this thing is the linear mass density. You know what? I'm going to replace this. I'm going to put this thing equals L. I'm going to do cursive L, M, D. We'll just call that linear mass density because that's easier than dealing with this fraction on the bottom. Okay, so this wants to know, well, oh wait, how would I get my force of tension? Oh look, I could do the weight versus the force of tension, and if this thing doesn't move, they balance out. So those two may equal out here in a big mg. So I'll bet, just really quickly, that your force of tension equals big MG if it's not accelerating, like if that thing's just stationary. Like if the mass is really heavy and pulls the string tight, so that would be like they would just sit there if it's a fixed situation. I'm gonna put an acceleration equals 0. Just a thought I had. Like that's leading me towards fixed. Okay, what's the difference about the 4 strings that would result in different fundamentals? Frequencies. Oh, I kind of already have that. Hang on, I got a black pen. The thickness of the string. So I'm going to circle kind of my original thing. Thickness of the string. And what would the thickness of the string cause that would be different? Well, look up here. This says a little m. That's not like a big M. So this is the mass per unit of length of the string. Look at that mass of the string. That's what the little m is. That's the mass of the string, so that's totally different. So if the thickness of the string is different, then the mass, I'm going to put mass of string, is different. I'm going to abbreviate different now. Okay, so I kind of cheated here because I typed, because it's really hard to write with the mouse. All right, so this is how I would have answered it. If the thickness of each string is different, then the thicker strings would have a greater mass for each unit of length. Therefore, the linear mass density, m over L, like they gave it, is different. This is because velocity equals lambda frequency. Therefore, velocity is directly proportional to frequency. Therefore, since this has been given up here, frequency is inversely proportional to the square of mass over length. I think that's a good explanation. I'm pretty sure I would have gotten full credit for it. So now for the last part. I kind of deleted what I wrote before. Sorry about that. So a student graphs frequency as a function of the inverse of linear mass density. Okay, so that means frequency would be your input, and linear mass density would be your output. Yeah, that graph is ugly. Hang on. Okay, so back to this one. A student graphs frequency as the function of the inverse of linear mass density. Okay, so I would look at this and look at my axes and see that even if I'm not great at math, my slope is not going to be linear. It's not going to be a pretty one-for-one like slope. It's not going to look like this because I have this square root here. So you don't have to draw the graph. I just kind of wanted to show you that. But I would say on this, let's say something about it not being linear because it's a square root function. Okay, so you could draw the slope on it if you're comfortable doing that, or you could just, you don't have to do that. You don't even have to draw the axes. I just restated that frequency is inversely proportional to the inverse of linear mass density. And I wrote, this is not a linear relationship. The slope of the graph would be parabolic. And that's how you do this problem.